Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus and introduce three primary rules that can help us virtually find the derivative of almost any function, provided that we know the derivatives of the smaller pieces of the bigger, more complicated function. These rules are referred to as the product, chain, and quotient rules. So up to this point, we already know that derivatives can distribute nicely over sums and differences of functions, provided that those functions themselves are differentiable. For example, if you have the derivative of e to the x plus x squared, we can just take the derivative of e to the x and x squared independently and just add those derivatives up, and that would be the derivative of the sum of the original function, in particular e to the x plus 2x. But the main question is, does derivatives behave the same way with products and quotients? That is, can you distribute derivatives over products? I.e., is the derivative of the product of functions equal to the product of the derivatives of functions, provided that those functions themselves are differentiable? Generally speaking, take a guess? No. So, if that's the case, obviously there should be another rule for the derivatives of products of functions, and indeed there is. And this first rule, which I'll present, is called the product rule. So the actual derivative of the product of two differentiable functions, f and g, is equal to the derivative of the first times the second plus the first times the derivative of the second. And obviously there's a couple ways you could write this. For example, you could also write this as f of x g prime of x plus f prime of x g of x, as they are the same exact thing because we have addition in the middle and multiplication is commutative, right? But I'm going to prefer to write it in this direction for a reason that may become clear in the near future. So let's just do a couple examples to sort of see what this formula says and how to use it. So example 1. Let's assume that we're interested in finding the derivative of the product of the functions x squared and sine x. As long as you know the derivative of x squared and the derivative of sine, you should be able to find the derivative of their product. So according to this rule, we have to start off with the derivative of the first, which is going to be 2x, times the second, which is sine of x, plus the first, which is going to be x squared, times the derivative of the second, which is going to be cosine. And that can be taken as the final answer. Obviously, you may be able to factor that answer, but generally speaking, that is the derivative of the product. Let's do a couple more examples. Let's assume we're interested in the derivative of e to the x times the natural log of x. And let's take that to be the natural log of the absolute value of x, so we can get practically all real numbers except for 0. So that's going to be equal to what? So it's the derivative of the first, which is e to the x, times the second, plus the first times the derivative of the second, and that would be your answer. Obviously here, factoring out e to the x may be more appropriate here, and that would just be the natural log of the absolute value of x plus 1 over x, but generally speaking, the first answer is technically the derivative of the original. Let's do just one other example. Let's do the derivative of the product of x squared plus 5x plus 6 times sine of x plus cosine of x. So obviously this looks a little bit more complicated than the others, but you can think of this as this function times that function. And as long as you know how to take the derivative of those individual functions, you should be able to take the derivative of their product. So this is going to be equal to what? So the derivative of the first will be 2x plus 5 times the second, and then that's going to be plus the first times the derivative of the second, which is going to be equal to cosine x minus sine x. Obviously, there's a lot of distribution you could do here and combining like terms and stuff like that, but technically speaking, that is the derivative of the original. The next rule might be the most important of the three for the three primary rules that we're introducing today, and that's called the chain rule. And it says that the derivative of the composition of two functions f and g, in particular, let's assume that g is inside the function f, And let's just also assume that f and g are both differentiable functions at the point x of interest. Then what you can do is you can take the derivative of the outside by keeping the inside the same, and then multiplying that result by the derivative of the interior function. Now, this rule may seem complicated at first, but after a few examples you should get it. So let's start off with a nice basic example. Let's assume that we have the derivative of the sine cubed of x, which is also an equivalent way of writing the derivative of the sine function cubed. Notice you have to first off identify which function is controlling the other. Notice that the sine of x is in the cubed function. So the exterior function in this picture is going to be x or something cubed. So what is the derivative of something cubed? So the derivative of something cubed is going to be equal to, and you can sort of think about it this way, what is the derivative of something cubed? That's just going to be equal to the 3u squared, and then the chain rule says we need to do the derivative of that something with respect to x, right? So the derivative of something cubed is going to be equal to 3 times something squared, and then we need to multiply that by the derivative of that something, and the derivative of sine is going to be cosine. And that would be the answer. Obviously, you can write this in a nicer way. You can write this equivalently as 3 sine squared x times cosine. But technically, the first answer is the derivative of that first composition, sine cubed x. Let's look at a couple more examples, since this is sometimes not as obvious. But this example might make it a little bit more obvious of who controls who. Let's assume we want the derivative of the cosine of 5x squared plus 6x minus 1. So here, which function controls who? We have the cosine function and this quadratic function. Obviously, the cosine is controlling or protecting the 5x squared. Therefore, the derivative needs to take care of the cosine first and then take care of the interior function. So the derivative of the cosine of something is equal to what? So the derivative of the cosine of something is equal to the minus sine of something. And then we need to multiply that by the derivative of the interior function, which is just going to be 10x plus 6. And that would be the answer. Let's look at a couple more. So example 3. Suppose we want the derivative of the natural log of the absolute value of 8x squared plus 6x minus 5. You could just take this as the natural log of the quadratic, but the natural log of the absolute value of the quadratic forces that inside or allows it to be negative without any interference with the domain. So who controls who? So the exterior function in this case is going to be the natural log function. The interior function would be that quadratic. So the derivative of the natural log of something is going to be 1 over something. And then we need to multiply that by the derivative of something, and that's obviously going to be equal to 16x plus 6. That would be your answer, but probably a more preferred way of writing this is just going to be 16x plus 6 divided by 8x squared plus 6x minus 5, and that would be the derivative of the original. Let's just do one more. Example 4. Suppose we want to do the derivative of e to the power of x squared plus 5x minus 7. You also may see some people write this as the derivative of exp of x squared plus 5x minus 7. So, what is the exterior function? In this latter form, it might be a little bit more obvious of which function controls who, because obviously the exp function is controlling that quadratic, but again, these two are equivalent. So this exponential function is controlling its input function x squared plus 5x minus 7. So we need to take the derivative of that and then multiply it by the derivative of that quadratic. So the derivative of e to the something is e to the something. And then we need to multiply that by the derivative of that something, which is just going to be 2x plus 5. That is the answer, but some people will like that linear term to be in the front. So you could equivalently write that as 2x plus 5 times e to the power of x squared plus 5x minus 7. Just to be safe, every time you're multiplying by the derivative of that interior function, it's always safe to put that in parentheses, because if you do not put parentheses around it, it's a completely different function. The next rule that I want to explore may look a little familiar to you. That's the derivative of x to the r is equal to r times x to the r minus 1. You may recognize this as the power rule, but notice now I am allowing the exponent of x to be any real number except for 0. And you may ask, well, why do you exclude 0? Because obviously if the exponent of x is 0, anything to the 0 power is equal to 1, provided that obviously x is not equal to 0, unless you've extended that to be 1. Right? So that would be just the derivative of the constant, which we've already proven to be 0, so we can sort of leave that 0 as a special case of this particular rule and treat it independently, right? But here, compared to the before, the power rule that we introduced, now we're doing the derivative of x to any constant power, right? So emphasis on the fact that this is any constant, not necessarily just a natural number. Now, is this true? Can really the exponent be pi, and I can bring pi down and say that's just going to be pi times x to the power minus 1? The answer is actually yes. So let's just give a quick proof of this to show how we can use the chain rule to verify that. So the derivative of x to the power of r can be rewritten as the derivative of the exponential of the natural log of x to the power of r. Because exponentials and natural logarithms cancel, so they're inverses. So this is actually equivalent. By properties of natural logs, we can bring this constant down in front of the natural log, and that's just going to be equal to the derivative of the exponential of r times the natural log of x. And now we have a chain rule problem, because here the exponential is the exterior function, and r times natural log of x is the interior function. So the derivative of e to the something is going to be e to the something, and then we need to multiply that by the derivative of that interior function, which is r times ln x. R is just a number, so it's just going to be equal to r times, and the derivative of natural log of x is going to be 1 over x. Right? So here, what do we have? So obviously we can rewrite that back into the original form, because that's just e to the natural log of x to the power of r, and that's going to be just r over x, and that's obviously equivalent to writing x to the r times r over x. We have r x's on top, we have 1x on bottom, so that's just going to be equal to r times x to the r minus 1, right? And that's the rule for which we sought out to prove. So let's just do a quick examples to show how we can use this generalized power rule to find the derivative of these power functions. So what is the derivative of x to the power of 5.2? That's going to be equal to 5.2 times x to the power of 5.2 minus 1, which is going to be 4.2, and that would be the answer. Example 2. What is the derivative of x to the power of pi? Again, the exponent is a constant, the bottom is a variable. Therefore, we can use the generalized power rule to take the derivative of this. So that's going to be equal to pi times x to the pi minus 1. Now you might not like that pi minus 1 on top, but it is just a constant, so do not give it any extra attention more than it deserves. Another example, suppose we want the derivative of the square root of x. Now it might not look on the surface that this is a power rule, but remember that the square root of x is just a fancy way of saying x to the power of 1/2. And 1/2 is a non-zero real number, therefore you can find the derivative of this via the generalized power rule. So that's going to be 1/2 times x to the power. Now what is 1/2 minus 1? So that's going to be equal to 1/2 minus 2 over 2, which is going to be minus 1/2. So that's going to be minus 1/2. Now although that is the answer, you could write this in a couple other ways as well, because this is the same as 1 over 2 to the power of x to the power 1/2, or equivalently 1 divided by 2 times the square root of x. And that's probably a more preferred way of how people will write it. And another example, let's assume we want to find the derivative of the fifth root of x. How would you do that? You may want to pause this video and try this on your own. So just like before for the square root of x, we can rewrite that fifth root of x as x to the power of 1/5. And that's going to be equal to 1/5 times x to the 1/5 minus 1, which is going to be minus 4/5. Obviously we can rewrite this as 1 divided by 5 times x to the positive 4/5. And if you want to write that in radical form, that's just going to be 1 divided by 5 times the fifth root of x to the power of 4, right? Typically, most people will probably prefer that way, but that is an equivalent way as well, and how you can use the generalized power rule to find the derivative of any power function. The next rule that we're going to introduce is the derivative of a to the x, which can be viewed as a generalization of the derivative of e to the x, but now instead of forcing the base to be equal to the constant e, now we're going to be allowing the base to be any constant typically chosen to be greater than 0. Right? So what is the derivative of a to the x? And again, let's mandate that a is a positive constant. So let's just do a quick proof. And again, we're going to be using a similar trick just like the generalized power rule, and we're going to be using the chain rule to help us. So this is going to be the derivative of a to the x is equal to the derivative of e to the natural log of a to the power of x. That x can be brought down, so we're going to have the derivative of e to the x times the natural log of a. Keep in mind the natural log of a is just a constant, therefore that is just a linear function. So via the chain rule, the derivative of e to the something is going to be e to that something, and then the derivative of that linear function is just going to be the slope of that line, which in this case is just going to be the natural log of a. Remember that e to the power of x times the natural log of a is just a fancy way of saying a to the x. Therefore, this is just the same thing as a to the x times the natural log of a, and that's what we sought out to prove. Now, you may be wondering, is this really a generalization of e to the x? Can I use this for any exponential including that? And you can, because that would just be the derivative of e to the x is going to be equal to e to the x times the natural log of e. And if you remember, the natural log of e is going to be 1, and we're just going to be left with e to the x times 1, which is the same as e to the x, which is the same answer as before. A similar theorem that is related to logarithms is the following, which I'll leave for you to prove, and that is the derivative of the log base a of x. That's just going to be equal to 1 divided by x times the natural log of a, now on the bottom. Very similar to the generalized exponential rule, and this would be the generalized version of, say, the derivative of the natural log of x, which is the same as log base e of x. Now let's just work through a couple examples for these new rules that the chain rule has given us. So, example 1. So what is the derivative of 5 to the power of x? So this is an exponential function since the top is a variable and the bottom is a constant. So that's going to be equal to 5 to the x times the natural log of the base, which is going to be 5, and that would be your answer. Now let's do the same for the logarithm base 3 of x. So now the derivatives of logarithmic functions are just going to be rational. So that's just going to be equal to the derivative of log base 3 of x is going to be 1 divided by x times the natural log of that base, which is going to be 3. The next function, let's just make things just a bit more complicated and combine things together. Let's do the derivative of the sine of x squared minus 3 to the power of x plus the log base 5 of the cosine of x. So obviously we have a function minus a function plus a function, so we can distribute the derivative over the sum and difference of those functions and take the derivatives of them independently. So the first one, we're going to be using a chain rule. We're going to be using a chain rule for that last function, obviously, and this is just a basic rule in the center because we just learned that rule. So what is the derivative of the sine x squared? So the derivative of the exterior function is just going to be equal to the cosine of x squared times the derivative of the interior, which would be 2x. And then we move on to this exponential, so the derivative of 3 to the x would be 3 to the x times the natural log of 3. And then for here, the derivative of the exterior function is just going to be 1 divided by the interior function, which is cosine of x, times the natural log of 5, and the derivative of its interior function will just be equal to the negative sine of x. Obviously, you should be able to present that in a nicer way, but technically speaking, that is the answer for which we seek. Let's introduce two elementary functions into our set of functions that are actually quite useful in practice. And these are referred to the basic hyperbolic trigonometric functions, which are represented by SINH and COSH, which is similar to sine and cosine, but some people will say sinh and cosh, or sunshine and cosunshine if you want a more happier name. So if you do not know what these functions are or what they look like, that's perfectly okay. You can take these as the definitions of these functions. So it's just a combination of exponential growth and exponential decay functions sort of averaged together. So let's just see if we can find the derivative of sinh and cosh just based on these definitions. So what is the derivative of the hyperbolic sine function? So we remember that the derivative of sine is equal to cosine. So one may guess, well, the derivative of hyperbolic sine would be hyperbolic cosine. Let's see. So that's just going to be equal to the derivative of e to the x minus e to the minus x divided by 2. That 2 is just a constant in the bottom, so we can just factor that out. And we're going to be left with 1 over 2 times the derivative of the difference, e to the x, minus e to the minus x. So we already know that e to the x has its own derivative, in particular e to the x. E to the minus x has a derivative of negative e to the minus x because of that minus 1 on the top. So that's going to change that sign to a plus. And obviously that is precisely the definition of hyperbolic cosine. So the derivative of hyperbolic sine is hyperbolic cosine. So that sort of matches with the circular trigonometric functions. Let's look at the other one. What would be the derivative of hyperbolic sine? So if you remember, the derivative of cosine is negative sine. So would the derivative of hyperbolic cosine be equal to negative hyperbolic sine? Let's see. So that's going to be the derivative of e to the x plus e to the minus x divided by 2. That half is still a constant, so we can factor that out. So we're going to be left with 1 half times the derivative of e to the x plus e to the minus x. That's going to be 1 half times the derivative of e to the x is itself. The derivative of e to the minus x is going to be minus e to the minus x, and that's precisely this definition of hyperbolic sine. So the derivative of cosine is negative sine, but the derivative of hyperbolic cosine is hyperbolic sine. So it's back to sort of where we started in that secular logic, I guess you could say. Now, let's just do a couple examples that sort of combines these with the other functions for which we've learned. So what is the derivative of the hyperbolic cosine evaluated at x plus the square root of x? So obviously the exterior function in this picture is going to be hyperbolic cosine. So the derivative of hyperbolic cosine is going to be hyperbolic sine of the inside times the derivative of the inside. The derivative of x is going to be 1, and the derivative of square root of x we already know is 1 divided by 2 square root of x, which you can obviously reprove, in case you forgot, by doing the generalized power rule on x to the power of 1 half. And that would be your answer. So let's just do another example. What would the derivative of the log base 4 of 1 plus cosine of hyperbolic sine of x? Now here we have a couple nested functions, right? Because notice that log controls this function and cosine controls this function. So we have a chain rule inside of another chain rule, and that's perfectly okay. We just apply the chain rule twice. So the primary exterior function in this picture is going to be log base 4 of this big inside, right? So that's going to be equal to what? So the derivative of the log base 4 of something is going to be 1 divided by something times the natural log of that base, and then times the derivative of the inside. So the derivative of the inside function is going to be equal to what? So the derivative of 1 is 0, and the derivative of cosine of something is going to be minus sine of something. Right, so that's the derivative of that green circle. And now we take the derivative of its interior function. So the derivative of a hyperbolic sine of x is just going to be equal to hyperbolic cosine of x. And that would be your answer. Obviously, you should be writing this as, for example, let's say negative hyperbolic cosine of x times the sine of hyperbolic cosine of x, all divided by, I guess you could say, natural log of 4 times 1 plus cosine of hyperbolic sine of x. That would be a more nicer looking answer, but technically speaking, this first answer is the derivative of the original. Now let us introduce the third rule for which we're focusing on today, and that is the quotient rule. So is the derivative of the quotient equal to the quotient of differentiable functions? Obviously, if the answer wasn't yes for products, the answer probably isn't yes for quotients, and indeed you would be right with that. So what is actually the derivative of the quotient? One can show via the limit definition that this is equal to f prime of x times g minus f of x times g prime of x all over the bottom function squared, right? So obviously, how are we going to prove or justify this one? Now, I'm not going to be using the limit definition. I'm actually going to be using the rules that we have already done before, in particular the product and the chain rule. So what I'm going to do just to make this notation a lot more nicer is I'm going to call u f of x, and I'm going to call v g of x. And therefore I'm going to call f prime of x the same as u prime, and g prime of x v prime, just to make the notation a little bit more easier. So an equivalent problem for which we seek to prove is going to be the derivative of u divided by v. So obviously u divided by v is the same thing as the derivative of u times v to the minus 1. So this is obviously going to be a product rule problem, and then followed by a chain rule problem, because notice that we're protecting v with that negative 1 exponent. So this is going to be equal to what? So this is going to be equal to the derivative of the first times the second, and then plus the first times the derivative of the second. So that's going to be minus 1 times v to the minus 1, and then times the derivative of the interior function, which is going to be v by the chain rule. Agreed? So this is going to be equal to what? So v to the minus 1 is the same as v to the power of 1 on bottom. Over here we have minus u over v, and then we also have a v prime there, right? So what do we have going on here? And also that should be a minus 2, so that should be a squared. So obviously to subtract fractions, they need to be the same denominator, so what I'm going to do is I'm going to multiply top and bottom of this by v, and this is just going to be equal to v u prime. Or I have to actually rewrite that order there just to make sure it matches with what we had before. So u prime v minus uv prime all over v squared, which is obviously the same thing as f prime of x g of x minus f of x g prime of x all over g, the quantity squared, which is obviously the derivative of u over v. Right? So it's the bottom derivative of top minus top derivative of bottom all over bottom squared. So let's just go through a couple examples on how to use the quotient rule. So the derivative of x squared plus 5 all divided by sine of x. Obviously this should be minimally defined as long as sine of x is not equal to 0. So this is going to be equal to what? So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Technically, you can do a little bit of distribution and maybe combining like terms with the top, but technically speaking, that is your answer. So let's just do another example. What is the derivative of x squared minus 5x plus 6 all divided by x cubed plus 7x plus 1? Again, what will this be? So it's going to be equal to the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Obviously, since these are all polynomials, you can distribute the tops out, and obviously if you want to go that route, be careful of that minus sign that will distribute to the right-hand expansion. But unless you're actually going to do something with this answer, I do not recommend expanding this, right? For example, if you want to find all x such that this is equal to 0, maybe expansion is preferred. But technically speaking, this is the answer to the original derivative quotient. Now that we have the quotient rule, which is sort of an alternative to using the product chain rule composition, Now we can find the derivatives of several other functions you may be familiar with from foundational mathematics, and the proofs of these require a little bit of trigonometric and hyperbolic trigonometric identity knowledge. And if you don't know, I'm going to mention it here quite briefly for you. But let's see if we can find the derivative of a couple other trigonometric functions, in particular tangent, cotangent, secant, and cosecant. So, what is the derivative of tangent? Well, you might not know the derivative of tangent, but you might know another way of writing tangent. And if you do know, then you should know that tangent is the same thing as doing sine divided by cosine. If you know the derivative of sine and cosine, you can find the derivative of their quotient via the quotient rule. So that's going to be what? So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, and the derivative of cosine is going to be minus sine, so careful of that minus, all over the bottom squared. So we have cosine times cosine, which is going to be cosine squared. We have sine times sine, which is sine squared. And we have that minus and that minus, which is going to be a plus. So that's going to be equal to cosine squared plus sine squared on top, all divided by cosine squared. And if you do know some of your special trigonometric identities, you should know regardless of the value of x, cosine squared plus sine squared is always going to be equal to 1. So we're just going to be left with 1 divided by cosine squared x. And if you know your reciprocal identities, 1 divided by cosine is the same as secant. Therefore, this is the same as secant squared x. So the derivative of tangent is secant squared. So, if you are familiar with these rules, then I invite you to try on your own to find the derivative of cotangent and show that this is actually equal to negative cosecant squared. Let's do the other two trigonometric functions that you may know. What is the derivative of secant x? So if you do know your reciprocal identities, then you may remember that the derivative of secant is going to be 1 divided by cosine. Obviously, you know the derivative of 1 in cosine, so we can use the quotient rule or maybe the chain rule by doing a cosine x to the negative 1 power if you prefer. So this is going to be equal to what? So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, which is the same as cosine of x squared or cosine of x times cosine of x. I'm going to prefer to write it like this, and the answer and the reason will seem obvious soon. 0 times cosine is going to be equal to 0, and we have that minus times a minus, which is a positive. So this is going to be equal to positive sine of x, or actually I'm just going to write it as 1 times the sine of x, all over cosine of x times cosine of x. Right? Now you can write this as just sine over cosine squared, and that would be a correct answer, but I'm actually going to write it in a different way. So from your reciprocal identities, you should know that 1 divided by cosine is secant, and sine divided by cosine is tangent. So an alternative way of doing the derivative of secant is actually just doing secant of x times tangent of x. And that would be sometimes the more common preferred answer. And obviously, if you do know these rules, then you should be able to prove on your own that the derivative of cosecant is equal to minus cosecant of x, cotangent of x, and you can prove it in a very, very similar way as the secant. If you're a little bit more familiar with the hyperbolic trigonometric functions, then you will also know that hyperbolic sine and hyperbolic cosine are not the only two characters in this story. We also have hyperbolic tangent, secant, cosecant, and cotangent in the story as well to find derivatives of. And the process for these is going to be similar to the ones for circular trig, except with a different family of identities to work with. So, similar to tangent, the derivative of hyperbolic tangent can be rewritten as the derivative of hyperbolic sine of x divided by hyperbolic cosine of x. And we already know the derivatives of each of these, so you should be able to find the derivatives of their quotient. So the derivative of so it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, and keep in mind the derivative of cosh is sinh, all over the bottom squared, which I'm just going to write as cosh squared. So cosh times cosh is cosh squared, and sinh times sinh is sinh squared, all over cosh squared. And One of your special identities from hyperbolic trigonometric functions is that hyperbolic cosine minus hyperbolic sine of a particular element x, regardless of what x is always equal to 1. So this is equal to 1 divided by hyperbolic cosine of x squared. And that obviously is going to be equal to hyperbolic secant squared of x, right? So just like trigonometric functions, the derivative of tangent is secant squared, and the derivative of hyperbolic tangent is hyperbolic secant squared. So there's quite a few parallels here, which is actually pretty nice. Using a similar approach, one can find the derivative of hyperbolic cotangent, and you should be able to show that that's actually equal to negative hyperbolic cosecant squared, which also follows a little parallel to the circular trigonometric functions before. Now, let's look at the other hyperbolic trigonometric function. Let's look at the derivative of hyperbolic secant. So, by definition, that's going to be the derivative of 1 divided by hyperbolic cosine, and that's going to be equal to what? So it's going to be equal to the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared, which I'm just going to write as cos x times cos x. So this cancels and goes to 0, and then we're left with this minus 1 and sine product on top. So that's going to be equal to minus 1 over hyperbolic cosine times hyperbolic sine divided by hyperbolic cosine. And that's going to be equal to negative hyperbolic secant times hyperbolic tangent. Now, here, it's a little bit different, and it's not quite parallel to the circular world, because the derivative of secant was secant times tangent. Here, the derivative of hyperbolic secant is negative hyperbolic secant hyperbolic tangent, right? So it's sort of the same in structure, but it has the opposite sign. So, question, what do you think the derivative of hyperbolic cosecant of x would be? Would that be positive since its complement is negative? Actually, no. The derivative of hyperbolic cosecant is also negative, but has the same parallel structure as before. In particular, hyperbolic cosecant of x, some people say cosec, times coth, or hyperbolic cotangent. Right? And those are the derivatives of all of your 6 primary hyperbolic trigonometric functions. Now, there's one last rule that I want to sort of mention, and it's referred to as the Leibniz product rule, and can be used as sort of a shortcut for the derivatives of or higher order derivatives of products of functions. So, for example, let's assume that we want to find the derivative, and let's go back to the basics again. What is the derivative of x cubed times, let's do hyperbolic sine of x just for fun, right? So that's going to be equal to 3x squared times hyperbolic sine of x, and then plus x cubed times hyperbolic cosine of x. Now, let's assume that I want to do the second derivative of x cubed times the hyperbolic sine of x. Obviously, that's just going to be the derivative of each of those products. So that's going to be equal to what? So let's do the first one first. So that's going to be equal to 6x times hyperbolic sine of x, and then plus 3x squared times hyperbolic cosine of x. So that's the first. And then plus, we're going to have 3x squared times the hyperbolic cosine of x plus x cubed times the hyperbolic sine of x. So that's the second. And sort of what do we have here? So if we rewrite this, we can write this as 6x times the sine h of x. And then what do we have here? So obviously we have some common terms here. You can write that as 6x squared, but I'm actually going to write it as 2 times 3x squared times cosine of x, and then plus x cubed times the hyperbolic sine of x, right? And that is the answer. And obviously, again, you could write that as 6, but I want to sort of make a point. Because generally speaking, if we want to find the derivative of f of x, g of x, and let's assume that we want to aim for the second derivative, one can find that this is actually equal to the second derivative of f times g plus 2 times the first derivative of f, first derivative of g, and then plus f of x times the second derivative of g. And one could say, well, is there a formula for the third? And obviously you would be right. So the third derivative of f of x times g of x would be equal to the third derivative of f times g plus 3f second f first g. And then the next coefficient, take a guess. Do you know what it is? It's going to be 3 also. F prime of x, g double prime of x, and then lastly g triple prime of x times f. Don't forget our f. And that would be the answer. Do you see a pattern? This pattern should look quite familiar to you if you're familiar with some other things that we've discussed before. In particular, take a guess of what the nth derivative of the product is going to be. And this is what is commonly referred to as the Leibniz product rule. So it's going to be equal to the sum from k is equal to 0 to n. Obviously, we have the binomial coefficients hanging out in front. So that's going to be equal to n choose k. And then we're going to have the n minus kth derivative of f times the kth derivative of g. And that would be your answer. So let's see if we can just put this to practice with a nice little example. Let's assume that f of x is equal to x to the power of 4. And let's assume that g of x is equal to, let's do something fun. Let's do sine of x. So this is going to be equal to what? So the first derivative of f is going to be 4x cubed. The second derivative of f is going to be equal to 12x squared. And then the third derivative of f would be 24x. The first derivative of g is going to be cosine of x. The second derivative of g will be equal to minus sine of x. And the third derivative of g will be equal to minus cosine of x. So this is sort of how you start to use the Leibniz product rule. And let's assume that the end goal was to find the third derivative of x to the 4 sine of x without actually having to work through each of those iterative products. So this is going to be equal to what? So we're going to start with the top, so 24x, times the original sine of x, times the associated binomial coefficient, so where are we at? So 1, 1, 1, 2, 1, and then 1, 3, 3, 1. So this is the 0th derivative, the first derivative, the second derivative, and the third derivative. So your coefficients should be 1, 3, 3, and 1. Right? So we have the third derivative times the 0th derivative of g, and there's an invisible coefficient of 1 in the front. And then we're going to be left with 3 times, now we're going to be moving up, so we're going to be moving to those two terms. So that's going to be equal to 12x squared times cosine of x. And then we have our coefficient of 3, and then we're going to be moving up again to those two terms. So that's going to be equal to 4x cubed minus sine x. You might want to move that sign in front of the coefficient of 3, but that's up to you. And then we're going to be moving on to the last term. So that's going to be equal to plus 1, and then times x to the 4 times minus cosine of x. And that would be your answer. The same exact answer you would get if you were to do the product rule 3 times for each of those sub-products. I hope you enjoyed this video. We definitely went through quite a few different rules, but up to this stage, as long as you know the derivatives of the basic elementary functions, you should be able to find the derivative of practically any combination via products, quotients, and compositions of those functions, regardless of how complicated. Hope you enjoyed this video, and I'll see you in the next one. Take care.